Let's get into an example where we have a power. So notice here that we have this second power floating around. And we know with polynomials that makes some sort of interesting things happen, and we want to see what happens here. So again, we want to look at local and global behavior, and our local behavior would be the zeros, the vertical asymptotes, and the holes in the graph. And you can have all of these. Any given x value should only fall in one of these categories, though. That's probably a really good thing to clarify here. So if you think you have a vertical asymptote at x equals 1, that's not also going to be a hole in the graph and or an x-intercept. It's only going to be a vertical asymptote. So for any given x value, pick one, but you could have different x values in each of these categories. And then for our global behavior, we're either going to have a horizontal asymptote or a slant asymptote, or it could be none of the above. And technically, there's things that are similar to slant asymptotes but aren't necessarily just a slant, but we're just going to look at horizontal and slant. Okay, so to find zeros, those are x-intercepts, and we do that by letting the function equal 0. The only way to make a fraction equal 0 is to make the top equal 0. So I'm looking at this and I'm saying, okay, I think I've got a 0, 0 going on for an x-intercept. You do want to double check and make sure that the denominator is not also 0, but if I plug 0 in for x, that is not making the denominator 0. So I think I'm good, just 0, 0. Vertical asymptotes, I do think I have a vertical asymptote. Remember, those happen, both of these two, in fact, happen when the function is undefined. So the denominator would have to equal 0. And at x equals 3, the denominator is 0, but the numerator isn't. So something only goes in this category if the top and bottom are both 0. And again, that should look like something that you want to do something with, because that would mean you'd have the same factor on the top and the bottom that you'd want to cancel out. And algebraically, go ahead and cancel it out. Graphically, there still was a domain problem there, so it does leave one little hole in the graph. For global behavior, let's see, we want to think about what happens as x gets really, really big, and you can do positive or negative for rational functions. The behavior should be the same on both sides. So what I'm seeing here is that on the top, it would be like having 4 times a million. And on the bottom, it would be having a million. Minus 3 doesn't really make much difference when we're talking about huge numbers, but a million squared. So notice that multiplying by 4 doesn't come anywhere close to multiplying by a million. So this is going to be a scenario where, since the degree is different, we have a first power on x in the numerator and we have a second power on x in the denominator. That 4 doesn't even matter. Kind of like the -3, the -3 didn't matter. The 4 doesn't matter here. We're basically having something order of magnitude wise in the ballpark of a million divided by a million squared. So you would cancel out like a 10 to the 6th from that, and you'd still have a 10 to the 6 in the bottom. So this would be like 4 over 10 to the 6. If you plugged in a billion, it would be a 10 to the 9 over 10 to the 9 squared. So when you canceled, it would be like 4 over 10 to the 9. The bigger the number you plug in, the bigger the denominator is, and this whole thing is going to head to 0. So this is the degree of the bottom bigger than the degree of the top, which will give you a horizontal asymptote at y equals 0. So let's look at a table again, just really quickly, just so you can see what's happening here. So I did set up the top and the bottom, so you can see the numerator is 4x and the denominator is x minus 3 squared. The yellow box, this first chunk, is looking at what happens near x equals 0. And I think it is a little interesting to see because, again, the numerator has multiplicity 1. So what you see when you have multiplicity 1 is that the sign changes. In this case, it was negative. The numerator was negative, and then 0, and then it switched to positive. Whereas the denominator doesn't have anything cool like that happening. It's just in the ballpark of 9. When you plug in exactly 0, the denominator is 9. If you plug in something a little to the left or right of 0, you get something either a little bigger or a little smaller than 9. So 0 divided by 9 is definitely 0, but interesting for us that multiplicity 1 does cause us to cross through the x-axis. So I am seeing that happening in my table. I also said there was a vertical asymptote at 3, and you can see that the denominator is 0, which makes the function undefined. But if you look, there's nothing very exciting happening in the numerator this time. It's just about 12. So we're taking 12 and we're dividing it by very, very small numbers. And when you divide by very small, very close to 0 numbers, you get very big numbers. This time, the denominator is squared. So what you see here is that even though the denominator hit 0, it didn't switch from positive to negative. It stayed positive. And just in case anyone doesn't know how to read this, a lot of calculators do this. This is scientific notation. So this is 10 to the negative 4.0001. I think I said enough zeros there. And this is the same. So these are tiny, tiny numbers. And when we divide, we're getting these really big numbers. So there's your vertical asymptote. X is changing very little, Y is changing a great deal, and that's giving us that asymptotic behavior. For the X going to plus or minus infinity to figure out our global behavior, you can see I plugged in, so 0 would be in the middle, so here's negative 10, negative 100, so these are getting more and more negative as we head to the left. And you can see that scientific notation happening again. The numerator is getting bigger, negative 40, negative 400, negative 4,000, so on. But the denominator is getting bigger faster. So while this is about 40, negative 40, we've got about 170. Then this jumps to negative 400, but this jumps all the way up to 10,000. 4,000 jumps up to, it looks like about 1,000,000. And then we hit the 10 to the 8, 10 to the 10. So the denominator is getting big much faster than the numerator. So we would say the denominator dominates this fraction as X gets really, really big negative. And you can see your Y values about a quarter, 0.03, 0.003, and now we're hitting like negative 4 times 10 to the negative 5th. So very, very small numbers. And then the same thing over here, as X gets bigger and bigger, the numerator does get big, but the denominator gets big way faster. And when the denominator wins, when it dominates the fraction, you're going to see the fraction getting smaller. If the denominator is big, the fraction gets smaller. So we are not getting a slant asymptote. We are getting a horizontal asymptote. And we did also note that our vertical asymptote has multiplicity 2. Our 0 does not. We expect to cross straight through at 0, 0, but our vertical asymptote does. So we will expect the signs to not change. It's either going to head to positive infinity on both sides of the asymptote or negative infinity on both sides. We don't know which without other help, but we do know that it's one or the other. So we could say, let's fill this in none. And I guess I could fill that in here too. Okay, let's go ahead and graph. And at first this might not seem like enough info, and remember you're always allowed to go in and plug in a couple of extra X values just to help you out. But we can get a pretty good graph with just this usually. We have an X-intercept at the origin. We have a vertical asymptote at 3. Always draw these in. X equals 3. And horizontal asymptote at Y equals 0. Okay, so this one is actually interesting. I think I probably will need one more point. Y equals 0. When your horizontal asymptote lies on the x-axis, it makes it not so easy to decide whether you should start above or below the horizontal asymptote. So I'm going to plug in, I'm going to just plug in x equals -1. That seems easy. Something on the left-hand side of your graph before you hit any local behavior. So just for getting started purposes, h of -1, I get 4 times -1 in the top, and I get -1 minus 3 squared, so -4 squared, which is 16. So I get -1/4. And that means I'm really close to the axis. I don't really care so much about the size of that number. I care a little, but not a ton. What I care about is that it's negative, so I need to be below the axis. So here's something really cool that happens that we need for now technology to tell us about. Calculus can help us spot this as well. What's happening here is we don't get to cross this horizontal asymptote. We don't get to cross the x-axis is actually the big thing until we hit 0, 0. So we know we have to be below the asymptote. And what happens is that sometimes your graph kind of ducks away just for a little while. and then has to come back up and cross. And again, this is just something I know because I've looked at a lot of these, but basically you should know that you have to have an arrow just below the axis. You should know you're going to have to cross through at 0, 0. So this getting dipped down below just a little will kind of help you make that shape. And then once we cross through, the next thing we have is we have to deal with the local behavior that there's a vertical asymptote at x equals 3. So I have two options. I can either keep heading up or I can turn around and head down. And I do get to make that choice without having to check anything else. The reason I get to make that choice is I know there's no x-intercept, so I can't turn around and cross the x-axis and head back down. So knowing there are no x-intercepts is just as helpful as knowing when there are some. So I am forced to head up to positive infinity. Again, you can always check a point if you get a little turned around, plug in, say, 2 and see what's happening. And then this multiplicity tells me that the signs won't change when I move from the left to the right side of that asymptote. So this has to also be heading up. It's like the 1 over x squared, right? This shape, we're getting one of those, and it could be right side up or right side down, or upside down, right side down. But we know that both sides do the same thing. So whenever you see a square, you're going to see that sort of shape showing up, that parent function shape, just near your vertical asymptote though. And then we're going to come down and we're going to flatten out and approach our horizontal asymptote because there is no local behavior left. The reason I know that I don't cross through my horizontal asymptote here is because I don't have an x-intercept. So this is something that messes with people a little. Horizontal asymptote is only global. The only thing I know based on my horizontal asymptote is that I should have arrows on the far left and the far right side of my graph. I can absolutely do things like crossing through the origin and crossing through that horizontal asymptote. You're allowed to cross over those over and over and over again if you need to. It's just that when x gets very big, you need to be getting very close. So horizontal asymptotes are only global, not local behavior. They don't tell us anything about the middle of our graph.